Hello and welcome to COP 4708. In this session we are going to continue with the relational model which will address the what's called normalization. Database normalization is the process of organizing the fields and tables of a relation database or relational database to minimize redundancy and dependency. Normalization usually involves dividing large tables into smaller relational tables. The objective is to isolate data so that additions, deletions, and modifications of a field can be made in just one table and then propagated through the rest of the database. And that will be via the defined relationships and the referential integrity constraints that is characterized by this database. Edgar Code, the inventor of the relational model, introduced the concept of normalization and what we know as the first normal form, then the second normal form, and the third in 1971. In 1974, Raymond Boyce and Edgar Code introduced the Boyce Code normal form, BCNF. A table is often described as normalized if it is in the third normal form. A table that qualifies as a relation is considered in the first form stage. A relation is in the second normal form if all of its non-key attributes are dependent on the primary key. A relation is considered in the third phase or the third normal form if it is in the second and has no determinants except the primary key. A relation is in Boyce Code normal form if every determinant is a candidate key. Modified data tables can be done by inserting, deleting, updating, which might result in inconsistencies, missing data, or outdated data. Normalization, or in other words, efficient normalization, will eliminate such anomalies. If the data is normalized, adding to the existing structure additional tables will be easy. The normalized tables and the relationship can serve as an informative data model to users. Normalized tables are suitable for general purpose query. This means any query against these tables, including future queries, those details cannot be anticipated, are supported. Even if we don't know what kind of queries will happen in the future, it still can be supported. So how can we transform tables into a normal form, eliminating modification anomalies from the relation? We can put all relations into Boyce Code normal form using the following steps. Step number 1, to identify every functional dependency. Step number 2, to identify every candidate key. Step number 3, if there is a functional dependency that has a determinant that's not a candidate key, then we need to move the columns of that functional dependency to a new relation, make the determinant of that functional dependency the primary key of the new relation, leave a copy of the determinant as a foreign key in the original relation, then create a referential integrity constraints between the original relation and the new relation to ensure the integrity of the data and to ensure consistency. Then we repeat step number 3 until every determinant at every relation is a candidate key. If there are more than one functional dependency, start with the one that has the most columns, and that will get rid of many columns from the relation at the same time. Let's look at the following example. In this table, we can identify the item number as determinant and the repair number as another determinant. Following the steps of the Boyce code normal form, we can identify functional dependencies. Then we identify candidate keys. In this case, the functional dependencies that I have, item number, can determine type and acquisition cost. Repair number can determine item number, type, acquisition cost, repair date, and repair amount. Based on these functional dependencies, then I can move the columns associated with the repair number into a separate relation. So I have a relation that's called repair, and I will use repair number, repair date, and repair amount in this relation. I will separate the other one, which is item, and that will be another relation that will have item number, type, and acquisition cost. I will leave the item number in the original relation. Based on that, now I have two relations, item and repair. They are connected with a foreign key, which is the item number. The item number is the primary key in the first relation, and the repair number is the primary key in the second relation, which is the repair relation. Now, to ensure the integrity of the data, we can add a referential integrity constraints, which will read as where repair.item number. That means the item number column that exists in the table repair must exist in the column that's called item number in the item table or the item relation. If we view the two relations or tables, they should look like this. A relation for repair with the primary key repair number and a foreign key item number, and a relation for item and the primary key is item number. Let's look at another example. We would like to normalize using BCNF the following relation, which is called SKU underscore data, SKU data table. And again, we start with the process of identifying the functional dependencies in the table. Then, once we have the functional dependencies, SKU as a determinant can determine SKU description, department, buyer. SKU description can determine SKU, department, buyer. Buyer can determine department. Based on that, I can split the relation into, or the table into two relations, the SKU data relation and the buyer relation. The buyer relation is defined by a buyer and department. The buyer as a determinant will be used as a primary key in this relation. When I move the buyer columns out of the main relation, I left the buyer in the first one to be as a foreign key. So the relation for the SKU data is SKU, and that's primary key, SKU description, and buyer as a foreign key. which will connect the two relations. To make sure of the integrity of the data, we use a statement which is where buyer must exist in SKU data.buyer. So the buyer column in buyer should be the same as the buyer column in the SKU data. If we view the two relations or tables, they should look like this. A relation for SKU data with a primary key SKU and a foreign key buyer, and a relation for buyer with a primary key buyer. A multi-value dependency occurs when a determinant determines a particular set of values. For example, employee has AA degree or bachelor degree or MS degree or PhD degree. There are multiple values for the same cell. Other examples will be employee siblings, employee phone number, or any other example that applies on different entities. In these cases, the determinant of multi-value dependency can never be a primary key, which means that the employee degree cannot be used as a primary key. In this case, the tables can be separated, or the relation can be separated into different relations. So we will have a relation that's called employee degree table or relation that has the information about the degree, and I can connect that relation with the original employee information relation either using employee ID or using employee name. So in summary, to eliminate the anomalies from multi-value dependency, we can separate these values into their own relations, which is known as the fourth normal form. The fourth normal form. That will be all for this session. If you have any questions, you can email it to Florida Online. Thank you and have a great day.